Hey everyone, and welcome. Have you ever wondered why water is, well, wet and liquidy at room temperature, or how a specific drug molecule knows exactly which part of a cell to latch onto? Well, the answer, a huge part of it anyway, is all about shape. Today, we're going to unlock the secrets of molecular geometry and learn how to go from those flat 2D drawings to the real 3D structures that control pretty much everything a molecule does. Okay, let's just jump right in. We all spend a ton of time learning how to draw Lewis structures, right? And they're great. They show us which atoms are connected, what kinds of bonds they have, but they've got one massive, kind of misleading limitation. They are totally flat. So what if that simple 2D picture is hiding the most important thing about the molecule? Its actual shape out there in the real world. And this right here shows you the problem perfectly. On the left, you've got the Lewis structure for carbon tetrachloride. It looks like a little flat plus sign, right? It's just a blueprint. But the reality, over on the right, is this awesome three-dimensional tetrahedron. And this is not just a cosmetic change. This shape is its destiny. It determines the molecule's polarity, its boiling point, and exactly how it's going to interact with everything else around it.
So how do we get from that flat blueprint to the 3D reality? Well, the answer is this beautifully simple but incredibly powerful idea called VSEPR theory. You can think of it as our official rulebook for unlocking that hidden third dimension and figuring out a molecule's true shape.
Now, before we can use the rulebook, we have to get one key term down, the electron domain. It's just a fancy way of saying a region where electrons are hanging out around the central atom. And here is the most important part, so listen up. Whether it's a lone pair of electrons, a single bond, a double bond, or even a triple bond, each of those counts as just one electron domain. That's it. One region, one domain.
So VSEPR, it stands for valence shell electron pair repulsion. Sounds super complicated, I know, but the idea behind it is something you already understand. Electron domains are all negatively charged, and what do like charges do? They repel. So these domains are going to automatically push each other away and arrange themselves around that central atom to be as far apart as they can possibly get. Seriously, it's just like people in a crowded elevator trying to get some personal space. They just naturally spread out. And the best way to visualize this is with balloons. I love this analogy. If you tied two balloons together at the center, where do they go? They point in opposite directions. That's a linear shape, 180 degrees apart. Tie a third one on, and they arrange themselves into a flat triangle, trigonal planar. But the second you add that fourth balloon, they can't stay flat anymore. They're forced into a 3D tetrahedron to maximize that space between them. This is exactly what electron domains are doing. Okay, this next part is super, super important. VSEPR theory actually gives us two different kinds of geometry. First, you have the electron domain geometry. That's the shape of everything, including the invisible lone pairs. But what we actually see as the molecule's shape is the molecular geometry, which is just the arrangement of the atoms themselves. So the process is simple. Figure out the electron geometry first, and then just pretend the lone pairs are invisible to see the final molecular shape. Now, I know this might sound like you're juggling a few ideas at once, but don't worry. There is a foolproof, 4-step method that will get you the right answer every single time. Let's lay it out.
Okay, here we go. Step 1, you've got to have the correct Lewis structure. That's your foundation. Step 2, just look at the central atom and count up the electron domains. Step 3, use that number to figure out the electron domain geometry, the shape with the balloons. And finally, step 4, look at your structure, ignore any lone pairs, and what's left is your final molecular geometry. That's the roadmap. All right, enough theory. Let's see how this actually works. It's time to put our 4-step method to the test with some real-world examples. Let's get to it and build some molecules. First up, the carbonate ion. Step 1, draw the Lewis structure. You see the central carbon has 1 double bond and 2 single bonds. Step 2, how many domains is that? Well, it's 3 regions of electrons, so 3 domains. Step 3, what shape do 3 domains make? Trigonal planar. And finally, step 4, are there any lone pairs on that central carbon? Nope. So the molecular shape is exactly the same as the electron geometry. Trigonal planar. Easy peasy. Okay, next up, the nitrite ion. The central nitrogen has a single bond, a double bond, and 1 lone pair. So how many domains? Still 3, which means our electron geometry is, once again, trigonal planar. But this time, step 4 is where things get interesting. One of those domains is an invisible lone pair. So when we ignore it and only look at the atoms, the shape isn't a triangle anymore. What we're left with is a bent or angular shape. See how that works?
Let's kick it up a notch with sulfur tetrafluoride. The central sulfur has 4 single bonds and 1 lone pair. That gives us a total of 5 electron domains. The shape for 5 domains is called trigonal bipyramidal. Now for the fun part. We ignore that 1 lone pair, and the shape that's left is called a seesaw. And I'm not kidding. A chemist somewhere looked at this and thought, hey, that looks just like a seesaw. And the name stuck.
Now, for 5 domains, there is one absolutely crucial rule you have to know. A trigonal bipyramidal shape has 2 different kinds of spots, 2 axial spots that go up and down, and 3 equatorial spots around the middle, kind of like the equator of the Earth. And the rule is this: a big, bulky lone pair will always go into one of the equatorial spots. Why? Because it gives it more room and minimizes repulsion. This is key.
So let's use that rule on chlorine trifluoride. The central chlorine has 3 single bonds and 2 lone pairs. That's 5 domains again. So the electron geometry is, you guessed it, trigonal bipyramidal. And following our rule, both of those space-hogging lone pairs are going to take up 2 of the 3 equatorial spots. So when we make them invisible, what are we left with? The 3 fluorine atoms form a perfect T-shape.
Okay, last example, the tetrachloroiodate ion. Central iodine has 4 single bonds and 2 lone pairs. That gives us a total of 6 electron domains. The electron geometry for 6 domains is called octahedral. Now, to minimize that powerful repulsion between them, the 2 lone pairs will go on opposite sides of the central atom, as far apart as possible. So when we make those lone pairs disappear, the 4 chlorine atoms are left sitting in a perfectly flat, square planar shape. So, we can now predict all the basic shapes. That's awesome! But VSEPR has another trick up its sleeve. It can also explain why the bond angles in real molecules aren't always those perfect, ideal numbers from our balloon analogy. And the reason, as you might guess, comes right back down to the power of lone pairs. This right here is the golden rule of repulsion. See, a lone pair is only being held by one nucleus, so its electron cloud is kind of diffuse and spread out. You could say it's fluffier. This means it pushes on its neighbors way harder than a bonding pair, which is being pulled tightly between 2 atoms. So the hierarchy is simple. The repulsion between 2 lone pairs is the strongest, followed by a lone pair and a bond pair, and the weakest repulsion of all is between 2 regular old bond pairs. And this table just shows that effect beautifully. Methane, ammonia, and water all have 4 electron domains, so they all start with that same tetrahedral electron geometry, where the perfect angle is 109.5 degrees. But check this out. Methane has 0 lone pairs, its angle is a perfect 109.5. Ammonia has 1 bulky lone pair, and its powerful push squishes the other bonds closer together, down to about 107 degrees. And water, with 2 powerful lone pairs, squishes that angle down even more, to about 104.5 degrees. It's a totally predictable trend. And just a quick final note on this. It's not only the lone pairs. Because they've got so much more electron density packed into them, double and triple bonds also act like bulkier domains. They'll push on single bonds a little harder, and that can cause some slight distortions in bond angles too.
Whew. Okay, we have covered a ton of ground here, from the basic idea of repulsion all the way to the fine details of bond angles. So let's put it all together in one powerful summary slide. Think of this as your ultimate toolkit for any molecular shape problem you'll ever face. And here it is, your VSEPR cheat sheet. This table connects everything we've talked about. You just start on the left, count your electron domains to get the electron geometry. Then, based on how many of those are lone pairs, you just follow the row across to find the final molecular shape on the right. If you can master this table, you've totally mastered VSEPR theory.
And there you have it. You now literally have the power to look at a flat 2D formula on a page and predict its true 3D shape in the universe. But really, this is just the beginning. The real question I want to leave you with is this. Now that you know the shape, so what? What's next? How does this geometry control a molecule's polarity, its reactivity, or its vital role inside a living thing? That is where chemistry gets really, really cool. Thanks for watching.